Okay, so if I can get everybody's attention. So good evening and welcome to the annual, and I think this is about the 15th, roughly, Emilio Segre Distinguished Lecture, presented each year by the Physics Department at Cal. Let me start by asking everybody to turn off your cell phones, please. Anybody who hasn't? This lecture was created through an endowment given to us by the Raymond and Beverly Sackler Foundation, and the intent was to bring cutting-edge experimental science in the great tradition of Nobel laureate Emilio Segre, and the intent was to bring it to a general audience. So we are honored and excited tonight to host Professor Arthur McDonald, the Gordon and Patricia Gray Chair in Particle Astrophysics and the Director of the Sudbury Neutrino Observatory, also known as SNO, which is a detector facility built in a nickel mine located about 7,000 feet underground at Queen's University in Ontario, Canada. SNO is actually a large collaboration with a lot of institutions involved, including in particular Lawrence Berkeley Lab. So I dare say there's some folks here tonight who have been deeply involved with SNO all along. So Art received both his bachelor's and his master's degree in physics from Dalhousie University in Nova Scotia, then got his PhD studying nuclear astrophysics at Caltech. He worked as a research officer at the Chalk River Nuclear Labs in Ottawa, Canada, and then was a professor of physics at Princeton University for about in the mid-'80s, after which he returned to Canada and to Queen's University. So the question driving a lot of particle astrophysicists these days, and in fact a lot of physics, is whether or not neutrinos have mass. And I have to say that when I was not just growing up, but through a good fraction of my career, the neutrino was the only other particle than light to believe not to have mass, and therefore the only particle other than light to travel at the speed of light. So it was with somewhat of a feeling of dismay that I learned that that's actually not true. And there were some momentous experiments done sort of at the end of the 90s and the beginning of the 2000s, which showed that the neutrino does in fact have mass. And Professor or Dr. McDonald has actually won one of the more distinguished prizes, one very akin to the Nobel Prize, called the Benjamin Franklin Medal, largely for resolving what was called the solar neutrino problem. So back in, again, when I was at least a graduate student, and actually quite a bit after that, there was a long-standing mystery of why not enough neutrinos were observed coming from the sun. And people felt that they knew the solar physics more than well enough to understand how many neutrinos should have been coming, and there was not nearly enough. And in fact, there were quite a large number of varying from really crackpot solutions and to science fiction stories to attempt to resolve this mystery of the missing solar neutrino. And it was discovered, as we now well understand, that neutrinos can morph from one type into another. And so the reason there were not enough observed is that they had simply changed into a different type of neutrino, which required different techniques to observe them. And Dr. McDonald was credited, he and Yoji Tsuka were credited with the discovery of the resolution of this long-standing problem. And so this issue of the solar neutrinos and the other neutrinos, the three types being able to morph into each other, has profound implications on our understanding of astrophysics, our understanding of cosmology, and of the nature of the fundamental forces in the universe. Dr. McDonald has also been awarded the Bonner Prize from the American Physical Society and the Gerhard Herzberg Canada Gold Medal for Science and Engineering, among a large number of other prizes. He continues his work today, where he's as director of the SNO laboratory, and is working on looking for another nearly invisible particle known as the WIMP, which actually stands for Weakly Interacting Massive Particle. And I don't think that's the topic of today's talk, but I'm sure he'd be happy to answer questions about that also. The neutrino, my understanding is that there is no chance that the neutrino resolves the missing mass of our universe. The WIMP, on the other hand, might. But the neutrino has all sorts of other consequences for cosmology. So with that background, we're really delighted to have Arthur with us here this evening. And we just want to welcome him and turn to our talk, Deep Dark Science.
Well, thank you very much, Francis, for that very nice introduction. It's a real honor and a pleasure to be here at at Berkeley and to talk about neutrino physics, although that's, I just checked, to say that it's like bringing coals to Newcastle is apparently a legitimate thing to say around here. It really is something, as you'll see, and as I realized when I was making up this talk, that Berkeley has excelled at for many, many years. And most of the illustrations that I'll end up referring you to are things in which Berkeley has played a significant role. And so I'll point out all those collaborations. So we're going to talk about deep, dark science. And what that means is that for many experiments that have turned out to be quite interesting, although extremely difficult, scientists have created laboratories deep underground, and the main reason for going deep underground is to shield out cosmic radiation, and the deeper you go, the fewer of those are able to penetrate and create effects in your experiments that would obscure the things you're interested in. And in those locations, study topics that are very fundamental, but typically involve massive and very technically difficult and challenging experiments in these dark underground locations. The subject of doing this apparently is not something that's occurred recently, although I'll show you that it has in fact expanded in its numbers considerably lately. So I'm going to describe some of the things that these crazy people, which of course are me and most of my collaborators, do when we go inside mines. The sorts of mines that we go in, here's one example, and this will figure in my talk in a number of ways. This is Snow Lab, as it is called, and it is near Sudbury, Ontario. It's an active nickel mine. Vale, which used to be, well, that's the company that bought Inco, International Nickel Company, is taking 5,000 tons of ore a day out of this same shaft that we use to get up and down to our laboratory being over here. This is where the Sudbury Neutrino Observatory was sited, and it's the place where we have an expanded facility to do a variety of things that I'll tell you about today. In Canada, the standard icon to use to show how deep you are is the Scien tower. You have to have an icon no matter where you are, and it's so we're about 4 Scien towers down. Now, what's happening in this country is also extremely exciting. The Sanford Laboratory at the 4850 level of the Homestake Mine, which is a historic site because it's the site where Ray Davis did the first solar neutrino experiments and made the first observations that led to the solar neutrino problem that I'll talk about a little later, is back in operation for this type of physics and is potentially going to be expanded to a very large future facility. In fact, I think there's a review going on at LBL today on this subject. Its depth is 7,400 to 8,000 feet, and that's measured as 6.5 entire state buildings. I have it on good authority that that's the way you measure it, is in entire state buildings, because my 7-year-old son, when we were at Princeton, took a school trip to New York and came back and told us that he had seen the entire state building. So you'll see there's another icon that's used in another experiment later on, but it's deep, and it's deep in order to get away from these cosmic rays. And we have been very successful both in SNO and now Snow Lab, and they will be very successful in Sanford and Dussel in avoiding such background radiation. And if you do, then you can do experiments that enable you to detect things that are only occurring on the order of once an hour, or in some cases, for some of the dark matter experiments, the objective is less than 1 per year as an observed particle without any radioactive background. And so the sorts of things that are studied are neutrinos. I'll talk about that. I will talk about dark matter a little bit towards the end. And rare radioactive decays, such as neutrinoless double beta decay, which is a major topic that leads from the sorts of understanding that we've obtained so far about neutrinos that Francis mentioned. And in doing these measurements, we can learn about new details of the laws of physics for very fundamental particles, and also, in many ways, basic details of the evolution of our universe. And so those are the things I'll try to tell you about today in the context of a wide variety of different technological approaches to doing these measurements. They're kind of wild and wonderful, and they're always pushing the frontiers of technology. And so you really have to have the latest in engineering and applied science, as well as the latest in ideas in fundamental science in order to do this work. I'm going to try to do this all with only one equation. So I was told I'm supposed to try to give a talk at that sort of level. So there will only be one equation. So one example of this, these massive, technically complex experiments is the Sudbury Neutrino Observatory that was mentioned earlier, which is 6,800 feet down, but itself is about 10 stories high, holding in its core about $300 million worth of material called heavy water, which we had on loan for $1, which is good leverage in any economic situation. This was back in the early 90s that we made the deal, and the results were obtained starting in 1999. And we're just in the process of publishing the final papers on the various phases of the experiment. This heavy water was contained in a transparent vessel 12 meters in diameter and looked at by 9,500 light sensors, which were themselves in an external water bath. And the idea was to try to get rid of the cosmic rays with the depth, but also to have graded radioactivity and to keep it extremely clean. And so the whole experiment was done with the entire laboratory as what's referred to as a class 2000 clean room. That refers to the number of particles that there are in a cubic meter of air. And so you're really trying to get rid of all the dust that could bring radioactivity into your experiment. And so keeping careful control on local radioactivity is extremely important. And so we managed to put together this 1 million piece experiment and have less than the amount of dust you can pile in your thumbnail on all of the pieces of this experiment. And that was essential in order to observe neutrinos without having any significant radioactivity. The neutrinos are observed by looking at bursts of light that are observed by these 9,500 light sensors that have about a 1 in 6 probability of observing a single photon of light if it's emitted in the center of the detector. And so that was pushing technology, and you'll hear a lot more about pushing technology later on. So neutrinos, what are neutrinos? What are we talking about here? They're not the sort of thing you hear about on the Today Show every day. Along with electrons and quarks, we think that they are the particle, well, as of right now, those are the ones that we don't know how to subdivide any further, and therefore they are basic particles. They come in 3 types, associated with with the electron and 2 heavier related particles called the mu and the tau particle. And they are an essential part of the standard model of elementary particle physics. They only feel a weak force, and therefore they can travel through matter, and only in the distance that light travels in a year do they have a significant probability of hitting something. And that's because they have to hit either an electron or the nucleus head on. So for them, matter is open space. And so that makes them extremely difficult to detect. But on the other hand, it also makes them very valuable for getting to some production sites, such as the center of the sun, without having them be stopped by the remainder of the material in the sun. And so if you can build an enormously, a massive detector and are able to detect them, in our case at a rate of about 1 an hour, then in fact you can make some very interesting experiments. They're also produced in the atmosphere by cosmic rays, and we'll also talk about that a little later. So this is what we think is the essence of the particle zoo these days. There are quarks and there are leptons, lighter particles typically, not feeling the strong interaction, which is represented here by this gluon. These, on the other hand, do feel the strong interaction. The neutrinos are one-to-one with the electron mu and tau. How does this fit into your normal experience with atoms and so on? Well, three quarks, up and down quarks, are put together to form protons and neutrons. Those end up in the nucleus of an atom, and the electrons go around the atom, and that's what gives you the standard material from which we and everything around us is formed. These other particles are formed in higher energy reactions, and neutrinos in particular only feel these carriers of the weak force. They are produced in various forms of radioactivity on Earth and in nuclear particle reactions which involve the transformation of a quark into another quark. And they are typically produced in association with the lepton to which they are associated. Now, the standard model, as Francis mentioned, had neutrinos with zero mass and never changing from one type to another as its essence up until a few years ago. And in fact, that's one of the things that we'll talk about today, is how it has been shown that zero mass and never transforming is no longer correct, no longer thought to be correct. And so, in fact, there's been a tremendous increase in the field of neutrino physics. I guess it starts actually back in the first century, we discover, but the real milestone that starts this graph, and this is a nice graph produced back in 2005 by a study called the Neutrino Matrix, which just shows the way in which the activity in the field has increased, and these days it would be, since 2005, even more substantial in terms of the activities. It starts back in 1930 when Pauli made a proposal for why, when you observe electrons emitted in beta decay, you don't get a monoenergetic electron, even though the difference in mass is very well defined in this process. And people worried about non-conservation of energy and a variety of things like that. But eventually Pauli said, well, maybe there's something that just is being emitted but not being detected. And he made a statement that has kind of plagued this field for years. I've done a terrible thing. I've invented a particle that cannot even be detected. But it solved that problem, and Fermi came along very shortly thereafter and christened these little neutral ones, or neutrinos, and came up with a wonderful theory that works really quite well. These neutrinos were first observed, actually, the antiparticles, the anti-neutrinos. And by the way, for all of those particles I showed you in the standard model, there are equivalent antiparticles that are thought to have pretty similar properties, except in the charge case, they would have the opposite charge. So they discovered from reactors the presence of neutrinos. Shortly thereafter, Bruno Pontecorvo proposed that, in fact, the properties of neutrinos might enable them to oscillate. It might enable them to change from one type to another by a process that ends up behaving like a sinusoid, oscillating back and forth between the types. And that led to a number of things which we'll discuss later on. A lot of these experiments are associated with that. But Davis, as a real pioneer in this field, set about attempting to detect neutrinos from the sun using a large tank of chlorine-containing fluid back in late 60s. And immediately started to see too few neutrinos compared to what had been predicted. And this is what led to what has been called the solar neutrino problem, as Francis mentioned earlier on. Now, there's a wide variety of different things which I will tell you about that are in this list, and I'll come back to this picture again with respect to attempting to follow up and understand that, and also understand neutrinos produced in the atmosphere that I mentioned earlier on. This question of neutrino oscillations, however, is the fundamental thing that we're going to try to discuss today. And so I'm going to try to show you with only one equation, as I said, what it is that's involved in this process of a neutrino of one type being able to change into a neutrino of another type, and why that is related to neutrinos having a finite mass. Now, it's an unusual, uniquely quantum mechanical situation that if you produce an electron in a certain, an electron neutrino in a reaction that puts it in a certain quantum mechanical state, it is not necessarily the case that it is only one mass state that it is associated with. It can be a combination of three different mass states, which in this field are very creatively entitled state 1, 2, and 3. In fact, it appears as though the electron neutrino, from what we know so far, has very little of state 3. That will come up later on in the discussion. But if you produce that neutrino as an electron neutrino by a reaction that produces it in that form, and allow it to travel through space, then what you find is that these mass fractions in here will propagate through space, and there will be changes potentially in the fractions of those components in the state simply due to the fact that they have a finite mass. And so if at some further distance you come back and you make a measurement of how many electron neutrinos are present, which really means attempting to understand in your measurement the degree to which the thing you are measuring looks exactly like that combination of colors, then you find, in fact, that that can have changed. And it can look a little bit like this combination, a little bit like this, and a little bit like this. And so there's a finite probability of observing fewer of these and potentially some of these when you make the measurement, simply due to the fact that the neutrinos have a finite mass. And so what you end up with, in fact, is an equation for how this takes place, and this is the equation I'm going to show you. And I just want to point out to you, because it comes into the majority of the experiments that we're going to talk about, that the oscillatory part of the experiment depends upon a quantity which is the difference in mass between the dominant mass states that are affecting this particular process times the distance over which they have traveled divided by the energy. So if you have a fixed difference in mass and you have a fixed energy beam, then it will be oscillatory in L, which is the distance over which it has traveled. The quantity that's out in front here is a quantity that depends on how big those different components of the different mass states were in the particular flavor that you chose to do your experiment. And if you're dealing with processes where you're going through dense matter, as you are in the sun and in the earth, then these equations can be perturbed, and you can have resonance phenomena in which the oscillation is not the dominant thing that happens, it changes. But in straightforward experiments where you have things propagating through air or open space, this is the oscillatory behavior that you'll observe. So what about neutrinos that are produced in nature, which are some fraction of what we're going to talk about today? They're produced in, as you go up in energy, produced in solar neutrinos, which these are the dominant high energy form. There are reactor neutrinos at low energy down around 3 million electron volts. These energies are, well, an electron has a mass of about a 500,000 electron volts. There are higher energy neutrinos produced in the sun. There are some neutrinos left over from all of the supernovae that have taken place since day one, because when a supernova takes place, a burst of neutrinos occurs. And in fact, there would be quite a burst on this scale, because they're all emitted in about 10 seconds or so. And that's another thing that people have detected and done excellent physics with. Of course, this extends up to very, very high energies. In fact, some of the experiments, I'll show you one with Berkeley involvement, looks for the highest energy neutrinos, in fact, the highest energy particles that have been ever observed. And it is thought that there are acceleration mechanisms in black holes and supernovae that can produce such things. But there's also a lot of neutrinos that are produced in the atmosphere by the interaction of those same cosmic rays we're going underground to try to avoid. And so there's a wide range of naturally occurring neutrinos, but there also is the ability to to produce neutrinos by reactions produced by accelerators and tune them in such a way that they are in a reasonably well-directed beam. You can choose whether you're dealing with, well, they're typically muon neutrinos, but you can also choose electron neutrinos and so on. And this is what you are attempting to study with these experiments. So let's start by talking about solar neutrinos, where a lot of these things are a part of this discussion. Davis found there to be too few. Kamioka confirmed that in the 1980s and in the early 1990s. Two experiments using gallium confirmed it as well for lower energy neutrinos. Super K did the same thing again. SNO came along with its results at the beginning, 2001, 2002, and very shortly thereafter, Camland, looking at reactor neutrinos, confirmed the parameters that are involved in the solar process with great accuracy. So how are neutrinos produced in the sun? Well, the nuclear reactions that power the sun inherently produce neutrinos, a variety of energies, and these are the neutrinos that are observed, particularly in a number of the experiments, the ones that come from the decay of boron-8, these neutrinos here. There's a range of energies. Up until the SNO results in 2001, 2002, every one of the experiments that had been done were either exclusively or primarily sensitive to the type of neutrinos that are produced in the core of the sun, electron neutrinos. And therefore, when too few of those were seen compared to models of the sun that explained how the sun burned and explained all of the physical properties of the sun extremely well, when too few were seen, that could either be because those models of the sun were incorrect, or because perhaps the neutrinos were changing into another type by this oscillation process or some other process that would result in fewer of the electron neutrinos being observed, but not necessarily in those other experiments would you be able to tell the difference between the two, because you just measured one thing and there were two possibilities. Now, the SNO experiment, looking at those neutrinos produced in the sun that are streaming through and about once an hour producing a burst of light that we observe in our detector, was designed to use this material called heavy water, which is used in the Canadian style of nuclear reactor. It has an extra neutron in the hydrogen nucleus. And in that situation, you can see two reactions. One in which the deuterium is broken apart, and then you get a burst of light with a particular characteristic that's sensitive to all neutrino types. And then a second one, illustrated a second ago, which can be distinguished by the pattern of light in your detector that comes explicitly from the electron neutrinos that are produced in the core of the sun. So you have the ability to observe the ones that were produced in the first place and see, in comparison to the total number, what fraction still are electron neutrinos at the time they've reached your detector under the Earth. And in fact, what you observe is that, what you observe, and I'll tell you that in a moment, but the way you observe it in the detector, in fact, is to observe, you see these little circles, they are a photon of light striking the set of photosensors that are surrounding this. This is an 18-meter diameter circle holding photosensors, about 9,500 of them, that are looking in at this central heavy water volume. By timing to nanoseconds, you can actually reconstruct where the light came from to within centimeters or so, within the heavy water volume, tens of centimeters in the heavy water volume. And by that way, you can be sure that what you're looking for, in fact, are events that came from the heavy water. To build this detector, for which I showed you the schematic, you had to go through a major process because the shaft and the cage or elevator that moves in that shaft was limited in its size. It's about 3 meters by 3 meters by 4 meters. And so this whole detector had to be cut into about 1 million bits, the largest of which was that size. You can see one of the slices associated with the acrylic sphere. It's roughly that size. It's sitting on a stand and being bonded in place. When you're finished, you have a beautiful transparent sphere in the middle to hold heavy water. And here's a major Berkeley contribution to this experiment, because we had a very big set of collaborators very instrumental set of collaborators from LBL. And that is the support structure and associated hardware that held the 10,000 or 9,500 phototubes looking in at the heavy water. And so you can see the scale of this. You can also see the fact that all of the individuals have clean suits that are similar to what you might see in a clean room for semiconductor fabrication. It was all done with this class 2000 everywhere in the entire laboratory in order to get that 1 gram of dust to happen. So everyone that came into the laboratory took a shower, changed into clean clothing, and we were able to control the dust adequately to get really good data. The picture on the left here is one of the best pictures of this experiment, including, it was taken by a photographer from Berkeley, actually, who poked the widest angle camera in the bottom of the detector. And here's the sphere holding the heavy water, and here are these 10,000 or so sensors. And this is one of the best pictures of Alan Poon I've ever seen as well. When he was a student at UBC working on this, Alan is a staff member at LBL and has been the analysis coordinator for the SNO experiment. Just one example of SNO in Berkeley, which is something you don't normally see around here. Actually, one of our collaborators from Irvine, when we were starting the experiment, was a skydiver and went out of his way to take a SNO insignia and to dive and have a photograph taken of it holding this so he could say snow over California for an unusual period of time. But this group, including Kevin Lesko and Rick Norman and Bob Stockstad, who was very instrumental in all that cleanliness activity, was a very important part of the experiment. And here you see actually that geodesic structure holding the phototubes being assembled in California when it was originally constructed before it went to Sudbury. So this is one example of experiments where Berkeley has been has had a very central role. I'll mention this in a number of cases of where Berkeley people, either here at the university or up at the laboratory, were collaborators. It was an ultra-clean laboratory. You can just see how shiny those floors were. I never was quite sure if it was good enough until my mother visited and said, "It looks quite clean, dear." And so that was the ultimate compliment. She'd never seen anything that I was responsible for that had looked clean before. So, this was a fantastic occasion back in 1998 where we had to take some real special activities in order to get Stephen Hawking underground. But this is the data that we were able to obtain after we had gone to all this trouble to get rid of radioactivity. And what you're seeing here is essentially neutrinos and nothing but neutrinos obtained at a rate of approximately 1 an hour over a 3-year period for one of the phases of the experiment, in which we actually put some salt in the heavy water. In order to enhance the bursts that come from all neutrino types, and through their form in striking the photosensors, we could distinguish them from the ones that came from the other reaction, which are sensitive just to electron neutrinos. And so out of the total, we could extract, we could separate the two components, and what we found is that the electron neutrinos are only about 1/3 of the total. And that then was the explanation, because we found that the total matched very well, this number here matched very well with the standard solar model predictions, the models of the sun. And the electron neutrinos, just as the other experiments had found, were only about 1/3 of the total. And 2/3 of them had changed into another type. And this was the first of what you might call what gets called an appearance experiment for neutrinos, where you actually, in the case of the of all neutrino types observe those other neutrinos as well. And so it's not just a matter of the neutrinos having gone away, you know where they went. They became these other active neutrino types, ones that can interact in your detector. And you saw an explanation for what had been called the solar neutrino problem. And that factor of 3 also, as you see, resulted in confirming the solar model with great accuracy. And these days, the accuracy on those measurements, particularly by this particular reaction in snow, are more accurate than the theory calculations for solar fluxes. And in fact, they're helping the theorists to understand some of the details of what's happening in the sun. Now, very shortly thereafter, and in fact, they were doing these measurements over the same sort of period as we were with snow, the Camland experiment, which had a very major Berkeley involvement, looked at anti-neutrinos, which were electron neutrinos as well, from many reactors in Japan, in an underground laboratory at Kamioka in Japan. And what they were able to observe with a similar size detector, but one containing liquid scintillator, was an oscillation pattern. This is I think the most recent data showing this oscillation pattern very well. And this is where this equation that I showed you, this sinusoidal equation, matches very well with the data. And it is very clear that this is oscillation that is happening. And if you put in the parameters associated with this oscillation, the delta m squared and the theta that goes in front of the equation, it matches very well with the parameters that you would extract from the solar physics that snow measured, except in the solar case, you have to take into account this interaction with the other electrons in the sun. And so it's quite remarkable how well the parameters are in agreement between these two experiments, and really makes one think that, in fact, one is understanding oscillations. And in fact, with the set of data that's been obtained so far, oscillations is really the only explanation. Now, atmospheric physics was also something that was being studied quite extensively, starting back in the 1980s. Kamioka 2, which is the first experiment at Kamioka, and IMB, that's an experiment that was also happening in the 1980s, saw an anomaly which was really confirmed very strongly by the Super Kamiokande experiment, and then confirmed by an experiment which shot an accelerator beam to this Super Kamiokande detector in Japan. What was being looked at was neutrinos that are produced in the atmosphere by the cosmic rays. And in particular, what they were looking at is the muon neutrinos that you observe as a function of this zenith angle, which really is a measure of whether, well, for example, the ones that come from the top here only go over a short distance, and then as you vary the zenith angle for the ones coming from below, you're varying the distance through the Earth over which they travel. And what was observed was really very nice, and this is, I think, again, close to the latest data in all of the observations they've made, where what you're plotting now is an oscillation where the parameter is length divided by energy. So they're fixing the length and varying the energy in this case. But what you can see is that the oscillatory pattern that they are looking for is matched best by the oscillation parameters in this case as well. And this is something that they first observed in 1998. There were some other possibilities, but oscillation was the best and continues to be the best. The other two possibilities are shown here as these other colored lines. But oscillation for atmospheric neutrinos was very strongly observed in Super Kamiokande starting back in 1998. And now has been confirmed also in the US by very nice experiments from Fermilab to the Minos detector in Minnesota. It's a beautiful experiment. You can see the size of it and the set of photosensors, all of which are about that big to give you the scale of it, and 10,000 or so of them as well. Now, I mentioned the high-energy neutrinos. What we've been talking about so far is experiments that are aimed at trying to understand the detailed properties of neutrinos themselves. There are other experiments, and this is the Icecube experiment, as it's called, which also has a major leadership role from Berkeley, where you now say, okay, I know something about neutrinos and how they behave. Let's try to use them as astronomical probes, because they aren't affected by intergalactic material. They aren't affected by intergalactic magnetic fields. They come in nice straight lines, and you can observe them up to the highest energies possible. And so this extremely technically complex experiment, which is beneath the ice at the South Pole, instruments roughly 1 kilometer on a side of ice, clear ice. It is very clear at these depths, with photosensors in strings, and looks for these high energy neutrinos. And this is an experiment that has been installing these strings over the last few years, and is, well, you can see the schedule here, and it's now up to 80, it will be up to 86 strings with 5,000 or so optical sensors. And they will look for they already are looking, but they will continue to look for the highest energy neutrinos in existence, and attempt to do astronomy with that. Of course, you can see this is a really international experiment, right? Look at the icon. It's the Eiffel Tower. Only 324 meters, though, so there would be many of those entire structures if you want to take the whole set. So far I've been talking about neutrino properties predominantly, and the sun, and neutrino astronomy. Let's talk for a moment about how neutrinos come into what we know about how the universe has evolved. You learned a lot about that in last year's lecture by Andrew Lang, and I'm sure in others as well. So you will know that the predominant model these days is that about 13 billion years ago, there was a Big Bang, which resulted in a major expansion of the universe. And it turns out that some of the atoms that we are made from, of matter, were formed in that original Big Bang. And some of them, majority of them, were formed in stars that were formed from material produced in the original Big Bang, and in supernovae, which are exploding versions of such stars that create the sort of energy to produce the heavier elements. This is also a major theoretical topic here at Berkeley, is understanding stars and supernova. This is, again, this comes from Berkeley, from the educational project here. So we start 13.5 billion years or so ago. It says 14 here. And for what you end up with is the Big Bang, in which energy is converted primarily into matter by forming particles and antiparticles in equivalent quantities, in equal quantities. Of all the particles that you can think of, and probably ones we haven't yet thought of because we've never had the energies on Earth to be able to produce them. We may see some new ones when the LHC really gets its experimental program going fully, but there has not been energies on Earth to see some of them perhaps since the original Big Bang. Up to the first 100 seconds or so, one was dealing with particles and antiparticles and so on. It is thought that back in this period there was an annihilation of a large fraction of the material between the matter and the antimatter, leaving just a small amount of matter, and I'll come back to that in a moment. But eventually from that matter, nuclei, quarks came together to form nucleons. Nuclei formed from those nucleons. The electrons were around, and after about 3 times 10 to the 5th years, you ended up with, in fact, atoms being formed. And then those atoms would clump into various structures, particularly stars and stars into galaxies and so on. And so you end up with the sort of wonderful structures that we see when we do astronomy. And there's a story that runs through this whole process of how we came to be where we are today that involves neutrinos in various ways. In particular, the number of neutrino species, 3 active neutrino species, enters very critically into the formation of these materials, these light nuclei, back in the early universe. And in fact, it was thought that there were only 3 even before this was confirmed very strongly in measurements made about 15 years or so ago. In addition to that, of course, we just talked about how we now understand in great detail the reactions, nuclear reactions that power the sun, which is a typical star. And we did that via neutrinos. It turns out there are also substantial neutrino processes that take place in supernova relating to the production of the heavier elements. There are processes that produce the heavier elements. Some of them involve neutrinos, and some of that involves the properties that we just learned about neutrinos. And so the physics that we're learning in the laboratory today, in some cases using astronomical sources, feed back very nicely into the understanding of astronomical things and also cosmological things. And so a new topic that we hope to address in a future set of experiments is in fact this question of what happened back in the early universe when you produced equal amounts of matter and antimatter and a large fraction of them annihilated. And because of a small asymmetry between matter and antimatter, you ended up predominantly with matter. And so experiments that go beyond what I've talked about so far to try to test this are things I'll talk about now. Again, strong Berkeley connection in these experiments. First of all, understanding the detailed properties of neutrinos using accelerators is a major topic that is being pursued these days. And the objective here ultimately is to try to be able to do experiments where you start with beams of neutrinos or equivalent beams of antineutrinos and look at whether there are small differences between these, which one hopes is something that could be fed into theories that would go back and come up with full explanations of what was happening back in the early universe. Secondly, there's a very rare decay process called neutrinoless double beta decay that I will talk about in a minute, in which, again, there may be the possibility of observing this asymmetry, but also it's a process where you can learn other properties of neutrinos that may be necessary in order to get back and understand what was happening back in the earlier universe, such as, is the neutrino its own antiparticle? So what do we know now about neutrinos? Let me start with that, and then I'll talk about what we're trying to know better. I guess here in the vicinity of Petaluma, I'm allowed to use a Peanuts reference. One of my favorite Peanuts cartoons is the one where Linus asks Sally, "How would you like to have your life to live over, knowing what you know now?" And Sally contemplates for 2 blank frames and looks at him and says, "What do I know now?" And so that may be the case here as well. I mean, I'm going to tell you what we think we know now, but the wonderful aspect of all of this is that there have been really great surprises. I mean, the whole history of neutrino physics and even this information is not what was expected theoretically before we get into the measurements. The fact that neutrinos have very small mass was expected, but the fact that they are all grouped together with a relatively small mass, either since all we know from the experiments we've done so far is the difference in mass between mass 1 and mass 2 and between mass 2 and mass 3, we don't know what order this comes in. Is mass 3 lower than these other 2? And we do know, actually, from the measurements made by Snow, actually, that in fact mass 1 and mass 2 are in that order. And that's because of this interaction with the material in the sun. It doesn't work unless they are in that order. But we don't know what's called the hierarchy, whether it's this or this. We don't know the total mass. We know that the differences are very small. There are some constraints on the total mass, enough for us to know that, as was said, neutrinos don't make up the bulk of the dark matter. We need to look elsewhere for that, and I'll come back to that. And we have a reasonable amount of information about what I have plotted here, which is going the other way from what I showed you before. These are the mass states, and what I've plotted is the fractions of the electron, mu, and tau neutrinos that it's in each one of those mass states. I've just inverted it. And here you'll see that one of the things we want to see in the future, and this is going to be key to future experiments that enable us to address this matter-antimatter asymmetry, we hope, is in fact this small component, this little red part, the amount of electron neutrino in mass 3. So that's one of the things we want to measure, and there's a Berkeley experiment that deals with that that is about to take place. Berkeley's also involved in Dussel in a very big way, and one of the places, in fact, a prime candidate for where one might look for that matter-antimatter asymmetry, assuming that that little red part is big enough, is in fact an accelerator beam from Fermilab to Dussel. And in fact, if you're using these beams and they go through the Earth, as they automatically do if you are going over any reasonable distance just from the curvature of the Earth, the interaction with the electrons in the Earth can in fact make a selection between these two choices. And finally, this question of what is the absolute mass scale is a very important one. And that can be addressed by experiments on tritium beta decay, or it can be addressed by something called neutrinoless double beta decay as well, which I'll tell you about. That experiment that's led by people here at Berkeley that looks for that little red part, he lied. He said he wouldn't use more than one equation. Can I get out of that by saying this is the same equation? It's just in there twice, because that's what happens when you put in all of the details. And what's interesting is that it gives you something that was observed in CAMLAND. If you happen to choose your L and E appropriately to emphasize the difference in mass between mass 1 and mass 2, and what is the subject of a very sophisticated experiment being mounted for China is in fact this term, which is the difference in mass between mass 1 and mass 3, and this quantity in front, which is that little red part I was telling you about. And Berkeley is one of the leaders of this Diabet project. Double beta decay is a very unusual nuclear process where in some nuclei you can have a situation where normal beta decay, which emits one electron and one neutrino, is energetically forbidden, but two electrons and normally two neutrinos could be emitted. And in those cases, there's less than 10 of the, fewer than 10 nuclei that can be used for this that are in reasonable abundance. You can also have a process if the neutrino is its own antiparticle, where effectively the neutrino that would have been emitted gets reabsorbed as an antineutrino and no neutrinos get emitted at all. That turns this beta decay process back into this monoenergetic thing that wasn't observed and led Pauli to propose neutrinos back in the first place. And then you would get, if you look at the sum of the energy of the electrons, a peak here that is indicative of the fact that this double beta decay is taking place. However, the lifetimes that are predicted for this process are greater than 10 to the 25th years, and therefore you have to collect 10 to the more than 25 things and wait for some period of time in order to get the statistics to work. So you could actually observe this. So you need big detectors again. It has to be down deep and clean in order to do the measurements, because background is a problem. It only happens if neutrinos have a finite mass, and it turns out that in this case that mass can be determined simply by measuring the rate of this process if you are lucky enough to observe it. So many experiments are being mounted to do this. One of them is Snow Plus, as it is called. At the point where we were trying to decide what the name should be, that movie, The Matrix Reloaded, had just come out, and we toyed with that for a moment. But it really is Snow Reloaded, because it turns out that you can do this experiment, a very nice double beta decay experiment, by putting material, liquid scintillator, in this acrylic sphere. You can get about 100 times as much light output. And if you put in one of these double beta decaying materials, in particular neodymium, you can get a very competitive and sensitive measurement simply by using same electronics and so on. It's really quite nice in terms of this green revolution that's going on. This is kind of the ultimate in reuse of things. There are two very nice experiments in which Berkeley is participating. One is the Majorana experiment, which uses germanium crystals. This is slated for the Sanford Laboratory. These germanium crystals, for which Berkeley is also expert in producing, give excellent energy resolution, and you can discriminate against radioactive background compared to these rather localized double beta decay processes in those detectors. And of course, tellurium oxide is another very nice material for looking for double beta decay, and Berkeley is a major participant in the Quarry experiment, which is taking place in Gran Sasso, that uses these beautiful tellurium oxide crystals, where the measurements are actually made within fractions of a degree of absolute zero in order to get the measurements. So a few words only on topic 3 with respect to evolution, and that is dark matter, and dark matter particularly. Let me just show you that this fits into a picture that has evolved over the last 20 years or so, in which we think that the majority of the universe, in fact, is either dark matter or dark energy being another topic you know about quite well here. In fact, it having been studied extensively. It is thought that the dark matter particles that we think make up on the order of 20-some% of the universe would not be neutrinos, and the best candidate for them, in fact, are supersymmetric particles, which are proposed in a theory that gives you the next stage of unification beside the standard model I referred to, and which may be observed at the Large Hadron Collider now that the energy perhaps exists to produce them. But also potentially were produced, well, we think were produced in the Big Bang, and that's what's giving us the astronomical effects we observe. And so we hope to measure those in one of these deep dark, in a set of these deep dark experiments as well. And so our universe is rather a humbling place right now. We are a small fraction of we as being made of matter, and everything we deal with daily is a small fraction of the total universe. The majority of it is thought to be dark energy, observed primarily through supernova studies and acceleration of the universe's expansion. Dark matter we hope to observe in the experiments I'll describe to you. We are, for a wide variety of different reasons, quite sure that these dark matter particles exist. If you simply look at galaxies that look like ours and look at the velocities of stars that are out on the outer limbs of these galaxies, they're traveling so fast that unless there was a substantial amount of unobserved, unglowing matter in the central region, they would simply fly off into space because there isn't enough gravity to hold them in. And so we're looking for particles which, for other reasons associated with the formation of such structures, have to be massive, much more massive than neutrinos. They have to be particles that were produced in the original Big Bang and survive this 13 billion years or so. So maybe we'll find them at the LHC. What we're proposing to do in terms of direct detection is very complementary to that. So let me tell you about a couple of techniques for doing this, one of them being the use of liquid neon or argon, predominantly argon, for the observation of the recoil of the argon nucleus after a WIMP has hit it. We know roughly what the velocities of these WIMPs would be from that information about our galaxy. WIMPs can be distinguished from other radioactive background because they make a very short burst of light compared to other things. And we're trying to get these, they're similar experiments in terms of their light sensors looking at a central volume, but much smaller so far, as you can see, up to about 3,600 kilograms, or nearly 4 tons of liquid argon. Sensitivity we're hoping for is on the order of an event per year. This is the new SNO lab, expansion of the laboratory where SNO was, and these are the 2 locations that are being prepared for 2 experiments of this type. And another location is ready when a decision has been made for a CDMS experiment, that is an experiment that has had a very substantial Berkeley leadership, where these WIMPs are observed and distinguished from radioactive background by observing both the ionization that happens in germanium detectors and the heat production at these ultra low temperatures near absolute zero. So SNO Lab that I referred to is an expansion of the area 6,800 feet underground in this laboratory in Sudbury into about 3 times the excavated volume of snow, involving several different experimental locations. The whole laboratory is clean again, class 2000 or so, and it's essentially ready to go. What's happening there right now is that there are a couple of experiments in operation in this area. The snow experiment is being converted, and we hope to have it in operation in 2012. Mini Clean and Deep 3600 are scheduled for 2011 and 2012. There are some smaller experiments, including another dark matter experiment, and future experiments in these locations, and quite a large future cavity. You can see, my mother would like this as well, I think, and this is just another picture of that large cube lab where Mini Clean and Deep 3600 will be, and it's about the same size as the location over here that's ready to go. So my conclusions: deep is good, cleanliness is next, and dark is pretty easy actually when you come down to it. You just close it all in. They're all necessary, and we can make some very interesting experiments, and we've made tremendous progress in the last 20 or 30 years in this area. And we're at a point now where what we'll learn in the future will also be contributing significantly to our understanding of the universe, as well as to neutrino properties and how they fit into the standard model at a fundamental level. Thank you very much.
So thank you very much for that lecture. That was wonderful. So I'm going to turn the microphone over to somebody who's going to run around and pass the microphone to people who have questions. So I will throw the floor open to questions.
Yeah, Tony Fisher, very interesting presentation. 40 years ago, I was in high energy physics at the University of Michigan. My question is this, though. With the neutrinos and the other subatomic particles, is there any way that we can use this with their high energy in neutralizing radioactive materials?
Neutrinos are very difficult. I presume everyone heard that question. Neutrinos are very difficult to use in dealing with anything that is large volume, simply because they interact so seldom. On the other hand, there are people who are attempting to use accelerator beams of other particles to try to perform transmutation of radioactive materials, and particularly to perform those transmutations such that long lifetime nuclear wastes end up decaying more quickly. That's the objective. I don't think we're here yet in many of these cases, but it certainly is a program that is of interest and being pursued.
Well, thank you.
Question from Cal. Berkeley.
There is some idea circulating that radioactive decay constants are not constants but are variable. And I'm wondering if you can elucidate on that a little bit and tell us how real that is and how that relates to what you're doing.
I don't know of any observed and confirmed data that shows that that is the case. But if you're wondering whether the laws of physics are pretty constant over many, many years, there are experiments that are done in studying the properties of stars that were formed many billions of years ago, and looking at the spectra of those stars to try to see whether, for example, a fine structure constant has varied with time. And the answer there is that it and also experiments those experiments show that the fine structure constant has in fact been constant to an extremely high degree of accuracy for billions of years. And so I don't think there is a clear evidence for fundamental constants changing. And whereas there are some experiments that sometimes wonder whether radioactive decay can be influenced by some other thing interfering with the radioactive decay, well, that, of course, can happen. You can stimulate radioactive decay by other processes. But I don't think there's any indication that there's anything other than a nucleus that is formed and potentially being able to decay, being identical to other nuclei in that form and exhibiting, therefore, an exponential decay over many orders of magnitude. In fact, measurements like that have been done here at Berkeley, and that observation of exponential decay extends over, I don't know how many orders of magnitude. It's certainly greater than 6.
How about Wayne? Olga, do you want to try shouting?
I can. I heard, so this is a question from a, okay, thank you very much. So I'm not working in neutrino physics, so this question may be stupid, but I heard that there has been some indication for a non-zero neutrino mass in neutrino-less double beta decay, and so assuming that these measurements are true and not artifacts, would these contradict observations of neutrino oscillations, or are they complementary?
No such thing as a stupid question, by the way. And that's a very good one. Yes, in fact, there is an experiment which is yet to be confirmed and is somewhat controversial, in which neutrino mass is, in which a finite effect is seen in neutrinoless double beta decay, according to the experimenters, and it would imply a total neutrino mass of on the order of 0.4 electron volts. That's really not in contradiction with anything else. Neutrino oscillations observe predominantly the differences in neutrino mass, and this would be simply the baseline to which those differences get added, and they are much smaller than that, and therefore all neutrinos would have a mass very close to 0.4 electron volts.
But isn't it kind of unlikely that the baseline is large and the differences are small?
As I say, the theoretical prejudices in this field as to what is to be expected have proven to be wrong in majority of cases so far. So nature is what tells you what's likely and unlikely, it turns out. Let's say that wouldn't be in any substantial conflict, for example, with observations that are made in astronomy to attempt to limit neutrino masses within a model. It would work there too.
So you mentioned for neutrinoless double beta decay that that would require a neutrino to be its own antiparticle. How would we reconcile that with something like conservation of lepton number?
Well, it would imply that there isn't conservation of lepton number in this case. That's the reconciliation. It would be observed in this circumstance, and that's a significant question.
So also, if your neutrinos are now have mass, it's gone.
Correct.
Is there such a thing as a sterile neutrino, a fourth flavor of neutrinos, or is that fantasy?
That's actually another topic. I mean, in preparing this lecture, obviously there are some levels of sophistication that I couldn't attempt to go into. And so what I tried to avoid is topics that are still somewhat controversial. There were experiments that took place at Los Alamos that observed neutrino oscillations with small amplitude that would be in a very different mass range than the ones that were observed for atmospheric and solar neutrinos. The only way in which you could reconcile that, since you only have two mass differences to work with in a set of active neutrinos associated with electron, mu, and tau neutrinos would be to postulate that there are additional neutrinos that don't participate in an active way. They're referred to as sterile. They would have to take place in a different interaction than the standard weak interaction we deal with. However, there were experiments that were done at Fermilab, the mini boon experiments, that appeared to show that this explanation of simple oscillations for these for this experiment that took place at Los Alamos were simply not tenable. There are other puzzles associated with those experiments, including another experiment that's recently been reporting that used the opposite, used the antimatter beam, anti-neutrinos rather than neutrinos, that show results that are more similar to what was seen at Los Alamos, but they are only at the point of about 2 standard deviations at this point in terms of the effect that they're observing. And so I would say the jury is still out on that. If in fact that is the case, then it adds a significant piece of physics to what we're observing here, because you'd have to come up with placing sterile neutrinos within the standard model and so on.
It was the same question. Okay. It was a good question.
What is the apparent mass or other property of the particle that may have been observed on the Hadron Collider?
What would be observed on the Hadron?
Well, you referred to some new experiment on the Hadron Collider.
No, I was saying they may observe something. And what is being considered is that there is a theory referred to as supersymmetry that may include the strong interaction along with the weak electromagnetic interaction in the standard model that predicts symmetries for particles that might imply that the lightest neutral ones of such particles, or one of such particles, might be the particle that was produced back in the Big Bang and survived for 13.6 billion years and is clumping in our galaxy and is in fact the dark matter particle that we're looking for. But they certainly have not observed anything yet, and it will take a number of years for them to be able to sort out what they're doing to see something that would have a signature like that.
Is that particle one that's normally called a neutralino?
Yes. That's right. At least that's one example. There are other ways in which you can achieve what's needed for dark matter by using things called axions, which would be exhibiting properties very different from these weakly interacting massive particles. They are not such particles, but they can achieve what is observed in different ways.
I have to say that it's an impressive set of questions that we have from the audience.
I have to say that too.
Sorry, I should speak into the microphone. That was a very knowledgeable set of questions that we had from the audience. Any other questions? Knowledgeable or otherwise? It's oh, yes.
Hi, I can't remember from my graduate school days if Majorana particle means it's your own antiparticle or not.
Yes, it does, yes.
And what is the situation with neutrinos?
Well, that's exactly what one would like to measure with neutrinos double beta decay. If it is observed, it implies that the neutrino is a Majorana particle. It's the explanation for how you get neutrinos double beta decay.
And is that what the Majorana experiment at Stanford is trying to?
That is the reason for the name. That's right.
Thanks.
Okay, any further questions? Yes?
I've already asked one.
Okay. It was a good one. You get to ask two.
Is it true that in supernova detection, the neutrinos arrive before the photons, and why would that be?
Well, Wick's a much better expert than I am in this subject, but let me try. The neutrinos, although they don't travel at the speed of light, travel very close to the speed of light, and therefore they come essentially instantaneously once they're produced and once they are able to escape from the rather dense matter that's associated with a supernova as it is expanding after it has, well, what happens is you get an initial collapse and then a bounce and it expands. And the neutrinos come out first, and it takes several hours before the substantial burst of light that comes, in some cases, help me Wick, with gamma rays produced in the nuclei that are being formed and that eventually get out, but it can take up to several hours for that to happen. So you aren't guaranteed that you're going to have a couple of hours, but because of that possibility, we have been a part of a so-called snooze network, supernova early warning system, where along with Super Kamiokande and a large experiment in Gran Sasso, we've set up a central computer where if there is suddenly a burst of events in our detector, and the event rate goes up about a factor of 1 million in things that look like neutrinos when a supernova takes place for a short period of time. And it's very unlikely that that's going to be caused by power fluctuations or something else in the lab in Japan, Canada, and in Italy, and now also at the South Pole with one of the experiments, Amanda, associated with the Icecube experiment, to try to see if we can, in fact, notify the astronomers earlier than otherwise that they should look. You can only tell about a 25 degrees or something like that, which is a large patch on the sky, but to try to warn them that maybe they should be looking at least. So.
Okay. Any other questions? All right. Well, I think in that case, let's thank our speaker again.